All right, so let's start our class today. This is a lecture 7, and we will focus on the topic of depth from video. Before we get into this topic, let's have a quick recap of what we discussed last week. So last week, basically, we learned about, well, the week before, we learned about fundamental metrics. And this fundamental matrix is basically based on epipolar geometry. When we talk about epipolar geometry, it means that it means a triangulation. So this is triangulation, correct? So when we heard about this word of triangulation, something that you come up in your mind should be a triangle. So this is the basic idea of triangulation. Basically, it's a triangle. And in this triangle, we have a dot there in the peak. So that dot is actually XW, a point in the world. And then you have an image plane, one in the left and the other at the right. And the other peaks in this triangle, this one and the other one there. The left one is called C bar, and the other one is called C bar prime. And C bar primes are what? What is the name of C? Anyone? What is C actually? What is C here? That in this drawing, what does it represent for? Represents what? Represents camera focal point. Yes, pinhole, the camera pinhole. So that one is C and C prime. And the green plane is an image plane, virtual image plane. And the intersection between the red and the green plane, so for example, this one here. So that dot is actually xi, for example, is a projection of your xw to image one. And the other one is, for example, that one. This is the projection of xw to the second image, to the right image, so which is called xi prime. Okay. And we also have another intersection between the plane and the triangle. This dot here called epipole. And the other dots intersection between the baseline of the triangle with the image plane is also called epipole, which is E prime. Any questions here? So you need to know about this. Right? So there is this, the whole thing here is called epipolar geometry. And in epipolar geometry, oh, by the way, I noticed that we are quite fast in our discussion. Means that this material that I will discuss today is supposed to be next week, right? And one of the reasons why it's quite fast is because I rarely heard any questions. Like, unlike the last year or last year before, there were more active in terms of asking questions. So if you want to make me slow down, which means that less material in the exam, right? Because otherwise the material will be more. So you have to slow me down by asking questions. Right? So that is the case. Because again, the depth from video is supposed to be next week. But because it's very fast, because there's no questions, then in the end of the day, there will be more material added into the syllabus. Again, if you have questions, ask me. Then we can have more discussion and more interaction. And it will be good anyway for your learning process. Right? Don't hesitate to ask questions. Okay, so anyway, so this is called epipolar geometry. And it is very important for stereo. So this is very important for stereo. Stereo is basically something that we want to have in the to get the depth. So stereo is something to do with depth estimation. And this system, two images looking at the same point is called stereo as well. And fundamental matrix, which is F, is important in two ways. One is that we have xi prime transpose F xi bar equals to 0. So this one is equation number 1 here. As you can see, it's the correlation between these 2 points here, xi and xi prime there. Although they are separate images, they have a correlation based on F. So F correlate xi and xi prime, right? And this is useful. This equation is useful. This equation is useful because if we do not know F and we happen to know xi and xi prime, for example, then we can compute F from this equation. So this equation is useful to compute F given x and xi prime. Okay, so that is the meaning of this. That why this equation is useful, because it can give us F from pair of images. The second useful equation regarding F is the application of F, which is F multiplied by xi bar equals to, anyone remember here? F multiplied by xi equals to epipolar line, which is L prime. So L prime is the epipolar line at the other side here. So given this one, given xi, by multiplying that xi with F, you will get that one. Okay, so this is the important equation here, number 2. And what is important? Why equation 2 is important? Anyone? Why equation 2 is important? Important actually, yes?
We need that line to faster find the
Exactly. To constrain the search space. Because if you have xi, actually you do not know xi prime. Or given any pixels on the left, you do not know what is the corresponding pixel on the right. You have to search. And searching the whole point on the right image is time consuming. So we want to constrain, we want to limit the search space. And to limit the search space, we rely on that blue line, which is called epipolar line. So this one is called epipolar line. And that epipolar line is very useful, right? Because it can reduce the search space significantly. And based on this line, we search the corresponding point of any pixels on the left, if we know f. So equation number 2 is the application of f. Equation number 1 is how we compute f. Okay, so this is the 2 equation that's important with respect to f. Now, any questions, anyone? Okay, so that's fundamental matrix and epipolar geometry. The next thing that we learn, was rectified images or rectified image. The property of rectified image is that if we have a stereo, the epipolar geometry here, the green is plain. So if you have rectified image and you have a point, and this point is xi, for example, then we know that for rectified image, the corresponding point will be on the horizontal line. And anywhere here will be xi prime. So this is the condition of rectified image. Means that the x and x prime here, x and x prime are not the same. But y equals to y prime. So y here, y prime and y are the same. Okay, so this is the condition, special condition of rectified image. So in other words, actually this red line and the blue line are the same thing. So these two lines are the same thing. If we know fundamental matrix, actually we can rectify any images. Okay, so given any image like on the triangulation, for example, we can convert those images to rectified image using fundamental matrix, because the red line and the blue line are the same thing. Any questions, anyone? Okay, so if there's no question, if we use rectified image, the search will be much simpler. And I can look at I'll show you the case, the real case of rectified image. Okay, so this is rectified image, so hopefully this. So anyway, so let's use this image here. So this is a rectified image. And in this rectified image, for example, if you want to know the corresponding point of this red dot on the left, Okay, so anyway, so if you want to find the red dot corresponding red dot points there to the image on the right, then if this rectified image, then you can have the blue line and we search through this blue line, right? The problem with this is that there are many, if you based on the pixel, if it is pixel based, the matching will be too many ambiguity because there's many white pixels. So assume that the red point there is actually RGB and there's a pixel, white pixels. And in this white pixel, there are too many white pixels on the right. So there is a lot of ambiguity. And to reduce this ambiguity, what do? To avoid this ambiguity, what is the solution? To increase the size of these pixels, means that we, instead of pixels, we use windows. And windows will have more unique characteristic, right? So we use window space. So this one, for example, patch size 5. If you use patch size 5, somehow we can get the depth using this disparity, using rectified image. Right? But this is quite noisy. Even 5 by 5 patch is quite noisy. But the good thing is that it's quite sharp. That's with patch size 5. So to reduce the noise, we use a patch size 35. And using patch size 35, now is much less noise, but it's less sharp. And if we reduce further, if we increase further the size, the noise will be much less now, but it's much blurry in terms of the depth estimation. And that's the problem. The problem is that, first of all, we do not know what is the number here that is appropriate. What will be the best number? Maybe 35 or maybe 15. Different image will have a different size, right? So we are trapped in this threshold. That is one thing. The other thing is that we decide 35, for example. If we assume 35 is the best, we apply this 35 for all pixels in the image, regardless whether they are complex or not. When I say complex, is that, you know, if you look at this image here again, this part here, the white car is not that complex in terms of the texture. And in this kind of text, in this kind of color or texture, we need to have bigger size. But if it is very complex texture, like the tree here or the leaves here, right? We don't need to have that big patch. Small patch will do because that small patch is already unique in terms of the characteristic of the pixels. So different texture, different depth, different texture will influence the size, the patch size. So it doesn't make sense to set one patch size for the whole image. So, and that's something that we want to solve. Two things. One is that we do not know what will be the best patch for each of these, for given an image. And more complex than that is that this patch depends also on the texture. So different texture will give you different patch size, even in one single image. And that's the problem that we want to solve. Okay. Any questions so far? So that's really important motivation for us to discuss about MRF, Markov random field. One thing that's also important here for this simple naive method is that what we do here with the patch size is a local operation. We do it locally. So for example, the depth estimation here for this particular location there has nothing to do with the depth estimation for that location. So A here has nothing to do with B. And this is called local operation. Local operation means that you operate or you calculate the depth of A independent from the depth estimation of B. And if you optimize this A, for example, without considering the optimization of B, is called local optimization. Okay, so this is very common in engineering. The simplest, the naive method will be local operation. But this is not something that we want, because the depth of A might have something to do with the depth of B. They might correlate to each other, right? And to optimize A, we might need to optimize B as well at the same time. And not only A and B, but every pixels in this image. The depth from one pixel to other pixels have to be considered, have to be dependent to each other. And this type of optimization is called what? It's called global optimization. So global optimization is more effective than local optimization, but it's more complex, more difficult mathematically. Why? As you remember what we discussed in, so that's the motivation there, local and global optimization. And we prefer to have global optimization, right? And in order to have this global optimization, we learn about Markov random field. And this Markov random field is part of graphical models. Graphical models have two types: directed graph and directed graphs, and undirected graph. Markov random field that we will focus on is actually part of undirected graph. Okay, so Markov random field is a specific type of graphical model, which is called undirected graphs. Okay, so now what is the basic concept of graphical model? What is the basic concept of Markov random field? So without Markov random field, without graphical models, actually we can do the global optimization directly. Well, I call direct, this is my own term, direct of global optimization, or naive global optimization, if we can say naive here. Naive optimization, global optimization, is that we connect every pixel with other pixels. So every pixels are connected. So this is called naive global optimization. Assume that we have well, 9 pixels here, 3 by 3. So we have to connect all of them. Well, it's very complex to connect all of this. So I just put some knot here. So this is knot, right? As a knot that can connect all these pixels. So it means that every pixel connect to each other. So let's take a simple 2 by 2, so that it mathematically can be simpler, right? So it means that you connect this in this way and you connect in that way. So this is the same as the knot. This is every pixels connect to each other, right? This means that we have to express mathematically as probability of x1, x2, x3, x4. So this is a joint probability of all the nodes here. Right? So when we say mathematical probability, it means that we want to choose x1, the value of x1, x2, x3, x4 that makes this probability function to be maximum. So we choose the probability that we choose x1, x2, x3, x4 values that make this probability maximum. So we have to choose the maximum one. What does it mean by this? Assume that xi, assume here that xi or any x only binary, right? Only 0 or 1. Simple binary problem. If this simple binary problem, again, what we need to do is that we have to know what is the probability of x1 equal to 0, x1, x2 equal to 0, x3 equal to 0, x4 equal to 0. So we need to know this. Aside from this, we also need to know number one. Number two, we need to know x1 equals to 0, x2 equal to 0, x3 equal to 0, x4 equal to 0. Equals to 1. This is another possibility. And there's a lot of possibility here, right? In the end, this is, I think, is 2 to 4. 2 to 4 is what? 16, right? So that will be 16 here. P, x equal to 1, x2 equals to 1, x3 equals to 1, x4 equals to 1. So once we have all this possible combination of this space, then we can compare and choose the highest one. So for example, if the probability of number 2 is the highest, then we know that the value of x1 equal to 0, x2 equal to 0, x3 equal to 0, and x4 equals to 1. And that's the optimum values for this graph. Is that understandable? So this is naive, direct optimization. As you can see here, the combination is a lot. And we have to choose one of them that is really the highest. But if you do this, what happens? If you do this, what is the problem? Anyone? If you do this, what is the problem? No one knows? Yes? Too many combination. Exactly. If this 4, n equals to 4, so n equals to 4, the combination is what? 2 power 4. If your n, normally if you have an image, what is the size of your image? If you have take a picture, what is the resolution of your picture? 1000 multiplied by 1000. 1000 multiplied by 2000, which is what? 1 million. So you can imagine that if it is n equal to 1 million, all right, this means that the combination that you have to compute is 2 to 1 million. So that's the situation that we have here. It can take forever to compute this one. And that's how the naive of global optimization is not possible. Practically, it's not possible. This is important. When I say important, you know what I mean, right? It will be in the exam. So if you don't understand, please ask, because it's really basic, important concept. Okay, so I assume that you understand this. So again, the naive global optimization is computationally intractable. Intractable means here it's very, very expensive and prohibitively expensive. Now, the solution is proposed by a Russian guy called Markov, which is the name of Markov in the field. Markov thought about this, and he said that the connection is important, but we don't want to be trapped in connecting all the pixels to each other. And what he thought is that, okay, so to simplify the case, for example, if you have 9 pixels, you don't need to connect one to each other for every pixel. What you need to do is just, for example, if you think about this X, for example, just connect this with the neighbor. So that's the concept of Markovianity. So this concept is called Markovianity. It's called Markovianity or local operation. So another example of Markov-Yanati in our daily life experience is that when you want to predict tomorrow rain or tomorrow weather, for example, whether tomorrow is rain or not, you don't need to consider all the time in the past. Actually, the weather tomorrow is influenced by today weather. It's also influenced by yesterday weather, also influenced by 2 days ago weather, and so on and so forth. Actually, the tomorrow weather influenced by all the times in the past. But if you connect all the time in the past for tomorrow, you will never be able to predict the weather because the computational is too expensive. So Markov thought about this, and then he said that to predict tomorrow, you don't need to consider the past. You can only consider today to estimate the weather tomorrow. And the today weather have to be estimated by yesterday weather. And yesterday weather has to be estimated by 2 days ago weather. So this is kind of local connection. And this local connection is described here in the undirected graph case, is that this becomes something like this. And this kind of graph is called Markov random field. Maybe you have heard another type, which is called Markov chain. How many of you heard about Markov chain? Yeah, so this is also very popular in engineering. Markov chain is the 1D version of Markov random field. So Markov random field, because its field is actually 2D, Markov chain is 1D. But in the concept, they are the same thing. So I don't want to explain the detail of this because I already explained that to you. In the end of the day, previously, for example, we connect without Markov-Yanati, you connect all this together here, right? And now you change that or convert this into that. You convert all the connection of pixels into Markov-Yanati kind of connection. And this process has a mathematical foundation. This conversion from complex connection into simple connection is called factorization. Using factorization, you can transform all complex connection into less complex connections. I already explained this in the last lecture. So this is an important concept here. This important concept, factorization. Because using factorization, it's now possible that you can have a less complex structure. Right, so Markov random field, in the end of the day, if you have P of not only X, but also observation D, right? So the graph is a bit different now. The graph is that you have D as well. So this is the graph look like if you have D. So the square are D, the observation, and the bullet, the green bullet, is the random variables, the things that you want to know the value. Okay, so this mathematically is described as based on cliques, and clique is defined as mutually connected nodes. So based on cliques, we can have probability of phi in instead of probability value, we use phi, and phi is actually xi di, where I equals to 1 until n, n is the number of your nodes, multiplied by j, neighbor of I, phi xi xj. Okay, so this is the definition of Markov-Randolph field. And as I mentioned previously, this mathematical formulation is actually describing the graph. And the graph is connected by local connection. So this is the local connection expression in mathematics. So again, this is an important equation, and you have to understand this. And based on the mathematical equation, we simplify the things because at the end of the day, we don't want to have a probability. If we can, we want to have the probability value, of course, because probability value not only give you X, but also give you the value of X, but also give you what? Uncertainty, right? That's the beauty of this mathematical expression. Not only that you know X, but you also know the probability. Oh, by the way, if you know the probability, how can you get X? If you know the probability here, P, how can you get X? Well, simply choose the highest one. There is as I mentioned again in the previous explanation here, choose the highest one, and then you get the value of X, right? For example, number 2 is the highest, then you know the number of the value of X. So probability answer 2 things, give you the value of X, but also give you the probability of this value. That's the beauty of this mathematics here. But computing probability is very expensive. So we don't really want to be trapped into this expensive computation of probability. And in the end of the day, for our case, for example, we don't need to have probability. Of course, if we can, it will be much useful. But because it's expensive, we reduce the complexity of the problem. We don't want to have P, but what we want is only X. So instead of P, we want to have X. So we want to have the best X, which is X star. And how we can get X star without knowing P? So we want to have X star without computing P, without computing P, X, T. What will be the techniques to find X star without computing P? For those who take pattern recognition should know about this. What will be the techniques to find X star without computing P? Not MLE, MAP. I will. I think it's a bit out of the scope to discuss MLE and MAP. But basically, this MAP because because there are 2 terms. This one is called prior. This one is called likelihood. So we actually have both of them. If it's MLE, we don't need to have prior. But actually, we have prior. So we use MAP. Right. So we use MAP. The solution here is MAP. So MAP is that we have X star equals to maximizing the posteriori. Maximizing the posteriori means that argument max with respect to X, we change the value of X and then find the posterior, which is X given T. This is called posteriori. The expression here is a bit different from the expression that we have. So posteriori is actually P of X given T here. Let's put it in different color. Okay, so equals to, using base rule, it is equals to P of X and T divided by P of T. right? So, and this part here actually the same as the same as that one. And this part here is the same as this one. In other words, the joint probability is proportional to the posterior. Posterior is proportional to joint probability. What we know is a joint probability. So what we know is this one, the joint probability. So this one, again, this one is called joint probability. Joint probability between T and X. And this one is again is called posterior. Now, because this one is argument max, if we want to maximize this one, we just try to maximize the joint probability. We can ignore this one because whatever you change the X, it doesn't influence the probability of D. Probability of D is constant with respect to X. So because of that, then we can say that this one is actually the same thing as R max X P of X and D. Okay. Any questions here? Now, then the rest is easy because we just use the equation there. Sum of I equals to 1, phi of xi di, j neighbor of I, phi xi xj, exactly the same as what you defined previously. Any questions here, anyone? Well, based on this, we know that we can change this into argmin X, and we don't like product. We just use sum over I equal to 1. FD is the inverse function of phi. They are not the same. FD is again the inverse function of phi. Xi di sum plus j neighbor of I fp xi xj. So this is the mathematical equation that you will use in your assignment. Okay, so the last one is the most important one because you will use this in your assignment. Okay, so far here, any questions, anyone? Yes. The minus log 5. Yes, minus log 5. Any other questions? Okay, again, in Markov random field, this equation here is called prior term. It's because it's from prior. And this one is called data term because this one includes the data, PR, in the computation. Prior term doesn't have the observation. It doesn't care about the observation. Okay, so this is what we discussed last week, right? Now, based on this equation, we can have a graph. So if the graph is simplified graph, so if we have a graph here, for example, only consider 2 by 2 graph. So we have x1, x2, x3, x4. Oh, sorry, the t is have to be there. Not only x, but now we have t, the observation. So I write in this way. All right, so then we have t. Right, and we have x1, x2, x3, x4, and then we have t1, t2, t3, t4. Right. So in this graph, what is the value of the edges, right? The value of these edges here have something to do with ft. So this one is fp x1, x2. So the connection between x1 and x2, the edge there is actually from fp x1, x2. And the connection between x2 and t2 is ft x2, t2. So based on this, ft and fp for every nodes, then we have a complete graph. A graph is called complete graph if we know the value for all the edges. If we know the value for all the edges in the graph, it is called complete graph. And because we have a complete graph, now we are ready for optimization. And the optimization is called graph optimization. And one of the techniques for the graph optimization, so based on this complete graph, so this is called complete graph, we want to have graph optimization. And one of the techniques for graph optimization is graph cards. So now let's discuss a bit about graph cards. So you see the storyline here, right? The storyline is that based on the mathematical equation, we can have a complete graph. And from the complete graph, we are ready for optimization. So that's why this equation is very important. Because without this equation, you cannot have a complete graph. And without complete graph, you cannot do optimization, which is global optimization. Okay, so any question here before I move further? Yeah.
In the end, we still use the formula of joint predicate to decide which axis.
You misunderstand me. We use NAP not because we want to avoid joint probability, but we just want to avoid to compute probability. You know probability? Probability, and I'm not insulting someone. That's not my intention. My intention here is that probability have a value, have a constraint, have a property. The value have to be between 0 to 1, and the integral of the probability have to equals to 1. That's the property of the probability that we have to follow. If we want to know the probability, we have to obey this property all the time. And we don't want to because it's very difficult. In other words, it also here essentially we don't use probability. We don't really compute the probability. We just try to maximize. So what does it mean by that? It means that actually there is a 1 over z here. Actually, I didn't express that here. That's actually a good question. Actually, there is a 1 over z. So to make this probability possible, without z, the probability will not be 0 to 1. Will not have a value between 0 to 1, because pi here is any value, any function. You multiply the function, it won't give you between 0 to 1, and the integral of this function will not equal to 1. So you need to have normalization z, and to compute z is very expensive. Why is that expensive? Actually, I already explained this last week. Z is actually sum of x1 over x2 over x3 over whatever x you have. For example, xn here, and then you have to compute phi xi di multiply us. If this product, I mean, if you just put log on that function, And then you have a, okay, so anyway, so we can have product or have sum. It doesn't really matter. So this one, if it is sum, then it's log phi, xidi, plus sum of phi xj. So we have to compute this one. And z is very expensive, as you can see there, right? It's loop, inside loop, inside loop, inside loop, inside loop, n times. If n is 1 million, then your nested loop is a 1 million nested loop, which is impossible to compute. So if you want to have probability value p, is very expensive because of z. So we don't want to have z. We don't want to have p. So what we do here is actually using argument max. Argument max means that you just want to find the maximum value. You don't want to know the value itself, but you just want to find the highest value. So what does it mean by that? It means that, so for example, if it is maximum without probability, for example, you can have the function like this, or maybe maximum value, maybe something like this. And this one can be 1,000. It doesn't really matter because it's just a function which is not a probability function. But if you have to make it a probability function, you have to normalize this. It means that you have to normalize this, so then it can be below 1 and maybe 0.4 for that peak. Right? The sum here will be equal to 1. So this one is the absolute probability value. But the maximum, the x-axis here, x-axis is actually x. And x here is something that we want to know. What is x here is x star. So regardless whether you normalize or not, the peak will indicate the same x. So 0.4 is the probability that we want if the ideal output P of x. And argmax means that you just want to find the max. This is argmax of Px. Argmax of Px give you x star. Is that clear? Okay. Okay. Yeah. Good questions. Good question actually. So then I can have the opportunity to explain the details in this case. Yes. Sorry again.
Because from the class last week, I remember that you said that the phi function, the phi,
Yeah.
it is actually the same as the.
Not the same, but proportional.
Yeah, regardless of the normal.
Yeah. So phi has to be proportional with Px. So phi x have to be proportional to Px. Yes.
Yeah. So how did you get the expression of phi x?
So, yeah, a good question. So now that's actually the questions how to get this FD and FP, right? So basically, you need to know about this one, argmin. So what we care now is to minimize the function. So we try to find the value of x. We try to find the value of x here that minimize the whole function. It means that if you want, so there are two terms here, right? And we want to minimize these two terms together. So let's focus on the second term first. That's the easiest one. For the second term, to minimize and assume that we have the label is the label of x, so xi here, either 0 or 1. And we want to minimize. Minimize means that fp is expected to be 0. Minimize means that fp, we expect fp to be 0. Now, if we say that assume that xi equals to 1, xj must be, if you want to minimize this one, xj must be 1. So in other words, how we can define fp now? Fp is simply fp x1 or xi xj equals to the distance between xj minus xi. This is how we define phi or fp in this case. Right? Agree with this? Okay. So that's how we deal with fp. Fd is a bit more complex. Fd, because now you have to consider the data term. Again, but the idea is that Fd has to be 0 whenever possible. So we have to define Fd in such a way that these two terms can make the equation to be 0. So that's how we define Fp and Fd. So for the prior, Fp xi xj, the simplest one is the distance between xi and xj. The one norm distance means that we encourage xi and xj to be the same. So xi and xj are encouraged to be the same. And this kind of idea is called smoothness constraint. Smoothness constraint. Why this is called smoothness constraint? Well, it becomes smooth, right? 1 and 1, 0 and then 0, smooth. There's no up and down kind of patterns in your pixels. Yeah, any questions here? This is important. This is not only important for your assignment, but also important for your exam. Okay, so this is important for your exam to understand how you can define the prior and what is the reason behind the prior. And that's for the prior. For the data term or likelihood, actually, so this one is another word, another term of likelihood. Is Fd, xi, di. So you have the observation now. Okay. So fi di, so there is a problem here in terms of the scale. Well, if it is the not noisy kind of example that I gave to you, so assume that you have black and white, this kind of image with text CV, for example, and then you have noise here, and then you want to remove the noise, and then you know that the value of this is actually black, for example. So this is a black pixels, right? So in this case, the idea of likelihood is that to just follow the data. If the data is black, then it should be foreground. So here in this particular problem, actually we have xi. So xi here, xi have a label either foreground or background, right? And foreground, well, in this case, let's make it easy. Foreground is 0 and background is 1. In other words, the foreground of 0 is black, and the background of 1 is actually white. Okay, so that is the meaning of xi, the label of xi. Is it understandable, the label here? So this is called a label, or the value that you want to estimate. Any question? If you don't understand, please ask, otherwise we will get lost. Any questions here, anyone? Okay, so now, yes.
Give an example of how you find it.
Wow, okay, so we will do that later. For the depth, it won't be binary. So for that, the value is up to us to define. The range is up to us to define. It can be from 0 to 1,000 or 0 to 1 million. It's really up to you. But of course, if this label is too much, it will be difficult to optimize. But that will be more than two labels. Yeah. Any other questions? Okay, so if there's no questions, that's the condition of the label. But aside from the label, we also have the data. And the data is actually DI. And DI, is a pixel value, right? So this one is actually pixel values. And in this case, assume that these pixel values is just black and white. Black and white pixel value. So DI actually have two sets. So DI has two sets. One is black, which is 0, 0, 0. And the other is white, which is 255, 255, 255. So that is that's the data that we have. Right? So if you look at here, the value of xi, which is 0 and 1, and the value of di, which is pixel values, they have gaps. They have a gap here. Gap in terms of the scale of the value. Means that in defining the function of fi di, we want to minimize this. We want to, if this one is to minimize. We encourage this fg to be 0. Minimize to be 0. Okay. So, and we want to know the correlation between xi and di. So we need to have a distant function. So so we want to have a distant function between xi and di. But we know that di and xi have some gap. Xi is only 0 and 1, but di has vectors, RGB vectors. So there is a gap between these two. So for that reason, we have to change xi. We have to transform xi into the same value as di. So t here, t capital T function, is to transform xi into di. So what is ti? So ti or txi is to transform this one into black or white. In this case, 0, 0, 0 or 255, 255, 255. So this is 0, 0, 0 if xi equals to what? Anyone? Xi equals to equal to 0. And otherwise, if xi equals to 1. So that's how we transform xi into the same scale as di. Right? So now we have the same scale now. The same here is in the same scale. There's no gap. Now, what kind of distant function that we want to have here? The same. We want to minimize. If possible, we want it to be 0. So the distant function that we want to define in this case, the distant function between t, xi, di equals to I mean, how to put it in the, because this is a vectors now. So di, so basically the easiest expression will be txi minus di. But this one has to be normalized. Is that understandable? So it means that you have the sum. Let me see. Yeah, it's fine. So TR minus TIR square plus TG minus TIG. So let's put this G here, square, plus T blue channel minus TI blue channel square. That's the meaning of 2 there. The 2 here refers to these 2. The 2 here means L2 norm, the Euclidean distance. The Euclidean distance is this one, the square root of the square. Okay, so that's the meaning. This is called Frobenius norm, a square. But anyway, that's just a name. So you know the meaning of this, right? Now you can have the distance. So if di, so the things that we want to find is xi. We do not know xi. So we have to choose xi in such a way the transformation of xi is the same as your observation, your di. So that's the function for distance between xi and di. And that's how we define the data term of the likelihood. Any questions here, anyone? So again, because we do not know the value of xi in this case, we assume xi equals to 0. If xi equals to 0, what will be f d xi equal to 0 di? Depending on your di, depending on your observation, you will have some value. So in the end of the day, you will have some real value here. Because now you know xi, you assume that xi equal to 0. Then you also assume that xi equals to 1. Then you have f d xi equals to 1 di. This is another value. Another value. Okay, so depending on your assumption, whether xi equal to 0 or xi equal to 1, you will have some real value there. So for 1 pixels from 1 xi, you have 2 possible values for the data term. If it is binary, if it is x1 and x2 are binary. Any questions here? So call this A, call this B. Right? We will come back again into A and B here. The value of this A and B. Or later on, you will know. Actually, we discussed this already. This one is actually S, and this one is actually T. In the soft sync graph, that become S and then become T. So in other words, if you look at the graph, again, if I simplify 2 nodes now, then this one is, for example, x1, x2. This one is d1, d2. Actually, when we talk about fd here, the value of fd here, s and t, actually there are 2 values here, which is s or t. S and t is the value here. There are 2 values for 1 node. Because you have to assume 2 things, when xi equal to 0 or xi equals to 1. The same as in this other nodes here. There are 2 values as well. So for every connection with the data terms here, you will have 2 values. So although you see there's only 1 edge, actually these 2 edges. Actually, there are 2 values in 1 edge. That one is for the data term. But for the priors, for the prior here, you have for the prior, right? For the prior, you have xi and you have xj. You have 2 nodes. And it means that this one is actually, you can assume xi equal to 0, xi equal to 1, and xj equal to 0 and equal to 1. And the prior terms that we defined is fp, xi, xj equals to xi, xj absolute value. So for fp, now the question for you, for fp, how many values that you will have? Is 2. What are those two? 0 or 1. So fp actually have two values, 0 or 1. 0 when they are the same, and 1 when they are not the same. Correct? So 0 and 1 here, it means that you have value 0 or 1 there. In your connection of fp, you have two values, 0 or 1. Is it clear? In the package that you will use, which is called graph cuts package, for your assignment, your second assignment, because it's always 0, when they are the same, it's always 0, then you ignore this, you ignore that. You only have one connection. Because the 0, 1 is assumed to be 0. But actually there is a 0 then. Okay? Any questions here? Why 1 is there, and although we know there is 1, why 1 is there, later on I will tell you that 1 is not necessarily to be 1. It's something to do with our weighted factor. So we can change this 1 into W. But I will later on, or lambda. I will tell you later on. So just assume it's 1. Any questions so far? So for the graph. So this graph, as you know, will be transformed into ST graph for the graph cuts optimization. For graph cuts optimization, we transform this into ST graph as T, x1, x2. Okay, so what is this? Is this f t x I equal to s, maybe s is equal to 1, for example, and t equal to 0. So x1 assumed to be 1, given dr, given 1. So the bottom one, ft xi or x1 equal to 0, d1. So that's the value that you put there. So s here becomes here, and t there, the value of t becomes here. All right. So we do the same for the other side. So the other side here we have ft x2 equal to 1, t2, ft x2 equal to 0, t2. Any questions, anyone? And the things here is equal to fp, and we only have one fp. So fp x1, x2 is only 1. You can just copy here. If there are two nodes and two edges, then you just copy and assume that on one pair. Any questions here, anyone? So now by having this, we have a complete graph in a complete source sink graph. So we have a complete ST graph. Okay, so now we have a complete ST graph. Any questions here? No? All right. So once we have this complete ST graph, once we have this ST complete graph, what can we do? What we do is to optimize this. And the optimization is called graph cut or max flow min cut. So once you have ST graph, when you have complete ST graph, once you have complete ST graph, then you optimize the graph, optimizing the graph using max flow min cut algorithm. Or another name of max flow min cut algorithm is Fulkerson Ford algorithm. So this is something that we learned last week, that if you have a graph as T for simple case, x1, x2. So for example, we have the value here 2, 5, 9, 4, say that this one is 1 and 1, for example. 1, 1. So now we have a complete ST graph. And how we can optimize this, as we know that we can just flow the water to, right, coming to the second pi. Now we have 9 here, but I think we can just use 5. 4 is here, 1 is there, plus 1 is there. Okay, and this one is already saturated. So it's saturation here, saturation. And this one is saturation, saturation. Saturation means that we can just do the cut here. So we can cut here. And the cost of the cut is the cost, the mean cut, equals to what here? 7. And max flow equals to, max flow is the red one, 2 plus 5, which is 7. And this is called optimum condition. Optimum condition. The optimum condition is when max flow equals to mean cut. Means that it's optimized. And if it's optimized, we know the label, because the label is x1 belong to S, x2 belong to T. So in other words, now we can know the label x1 equals to S, x2 equals to T. S equals to, what is the first one? S is what? S1. And T equals to 0. 1 equals to background. This one is foreground. So that's how you know the label. And now, okay, any questions here before I continue? Yes.
So S and T is like two values that ground or foreground.
Yes. So this is a binary labeling. It is not binary. That will be more complex. Right? It is called multi-label graph cuts. So this is called binary graph cuts. And multi-label graph cut is much more complex. This one is guaranteed to be optimum. You can have a global optimum. But multiple labels doesn't guarantee you to get the global optimum. It converges, but it doesn't guarantee you to have global optimum. Because that one is NP hard. Anyone here familiar with NP? It's a complexity. In computation, there is a complexity cost. And this one, if it is multi-label, it is NP. Means that if you want to find the optimum one, it will be very, very, very expensive. But anyway, so I will stop there. Yeah, this is only binary label. Now, the most important thing is that when we get back into our earlier discussion, that we want to have a global optimization. And now the question is, why this one is a global optimization? Well, when you have multiple nodes and you define in this way, so for example, if you have multiple nodes, right? X1, X2, X3, X4, X5, for example, you have S here, and T there. That will be the connection that you will have. And to find this value for x1 and x until x5, you actually have to flow water. Your flowing water is going in this way, going globally. Maybe I'm not sure what will be the path, but this will be the possible path. Means that the optimization to know x1, for example, you need to consider x2, maybe x3, maybe x4. To find the value, the optimal value of x4, you need to know the value of x3, x1, perhaps. So that's why this is called global optimization. Any questions here? Another question that is also important in the earlier discussion. We know that in the earlier discussion that we want to have this X, the patch, to be adaptive. If it is textured, then it is small. If it is non-textured or textureless, it has to be big. Right? It's adaptive. So here, it becomes adaptive automatically. If it is needed, for example, if the graph needed to have more information, it will evolve more nodes. But if it is only small, for example, in this case, we only have the flow, for example, it's only this flow. So the flow is only this way for 2 here, right? So it doesn't get the involvement of other nodes. So the size, whether the pixel is involved or not, neighboring pixel involved or not, is now become adaptive. It's automatically done by the global optimization. We don't really put a certain number of thresholds for the size of the connection. Right? So that's why this is much more sophisticated in terms of the application, but more importantly also mathematically. Right. Any questions? So for those who are taking pattern recognition, right? At least in the first half of the course, I suggested a book called PRML, Pattern Recognition and Machine Learning. And the graphical model, Markov random field, is also explained or discussed in that book. It is, I think, chapter 9 or chapter 10, perhaps. If you happen to know or to have the book, please take a look at that chapter for graphical models in PRML, Pattern Recognition and Machine Learning book. Okay, any questions here? Yes.
Is it possible as T roots it means the same action with both assets, so it won't have
You have to cut an edge in any case. That will be the case that you have to cut. There will be there's ambiguity perhaps, because there, both of them are saturated. So here, for example, 5, 5, both of them are saturated, for example. Then you have to choose one of them, and you have to choose the most optimum one. The most optimum one means that this optimum condition here. Yeah, you always end up with choosing one of them. It's not possible that this is not saturated and this is not, or not saturated, because if it is not saturated, for example, after the counting, for example, 5, and then let me make it clear. So the original one, for instance, it is the value is 5, and the value is 4, for example, right? And then you put the water 2, and then here is 2. In this case, you cannot cut, but it is not optimum yet because you still have a water to flow. In this case, for example, you know, you have to put 2 and 2 here, and this is becoming saturated, and then you have to cut. So if you cannot cut either of 2 sides, then it means that it's not yet done. The flowing of the water is not yet done. It's not, the flow of water is not reaching the optimum situation.
What about like?
Yeah, so actually I gave you the example last week. So if you look at my explanation last week, right? So this is the explanation last week. Which one? So this one, this is the example last week. So you have 5 and 3 here, both of them are saturated. So how can we choose? So, well, basically you have to, you know, number one here, the cost will be 10, the minimum cut will be 10. If you choose number 2, the minimum cut will be 8. And we have to compute the max flow. And the max flow is actually 8. So this one is not the optimum one. The 8 will be optimum one. So in this case, you have to cut number 2. There's no other choice. Okay. Do you want to try this again? We can try this again. Let me see. Right. So S P x1, x2, x3. Okay, so the number here is 5. Not 5. Yeah, 5, 8, 2, 4, 1, 1, 3, 3, 2, 4. And if you compute this one, let's put number 5 here. 5, you have 3 here, right? 2 going that way, and then this one is saturated. So this one saturated, you cannot use it anymore. And then you continue with 2 here, 2 there. This one becomes saturated, this one is not. And 8 here, you cannot use all 8 because what will be the possible value that you have to put? 1. So this is 1. You have to use that 1. So the saturated node H is this one. So in that case, there's no ambiguity for this one. You cut that one. No ambiguity here. Cut this one. Cut number 1, not the 3, and cut this one. So X3 belongs to S. X2 belongs to T. So X1 has ambiguity there, right? So you have to find the optimum one, and the optimum one, we know that this one belongs to T. So you have to cut it. Okay, any questions, anyone? When it is minimum, yes. Because we minimize. Remember that in the beginning, very beginning here, no, sorry, not this one. This one, we want to minimize the function. So we choose the one that minimize the nodes. Any questions? Sorry? It is not 4. What do you mean? If there is no saturation? What do you mean by no saturation? It's actually asked before. If it is, I'm not really sure if your question is the same as the question before. Means that these two node S and T connection are not saturated. I don't understand. Okay, sure. All right. Any other questions? Yes.
I think when you do the new class, you just count all the separated patterns.
Yeah. Yeah. So that's the definition of residual graph. When the graph equal to zero, that the zero is actually you have to cut. Remember that this is a simplification. Actually, there are three graphs. So there are three graphs: capacity graph, flow graph, and residual graph. So the proper way is to have these three graphs. Any questions, anyone? Okay, so if there is no questions, actually this is just a recap of the previous week. But it's good. I mean, I try to slow down because otherwise it will be too much material to teach and also for you to learn. Okay. So let's have a break, 15 minutes. So we start again the second session, 15 minutes to 8. Let's have a break.
I have some questions. As you said before, the line between X y and 2 is FPX, I, and XJ. So, and it only could be 0 or 1. So why there?
Oh, this is just a given example.
It's not that.
It is not our case. This is just a general discussion.
And I still couldn't understand why FP could be equal to the distance between F and XJ.
Because we want to minimize the function here to be 0.
But the definition of FP is minus log phi.
Yeah, but phi can be any function.
We suppose it could be proportional to P, but
Yeah.
we define it as a distance.
Yes.
And I'm still a little confused about, well, you said the method to get the complete graph by MAP, but
No, MAP, MAP can give you the complete graph. This MAP, this MAP function, right?
yes.
Can give you the complete graph.
Oh, I'm a little confused about that because from MAP we could get the value of X to
No, MAP you can have FT and FP. First, using MAP you can have this value FP and FT. This is the equation of MAP, right?
yes.
So you with this formulation, you have the tool, the mean to get FT and FP.
By this.
Yeah, definition of this. So then, by definition of this, you can have a complete graph.
So we couldn't get X from MAP.
We can. In the end, if you optimize this graph, you get the value of X, right?
But firstly we get FD and MP
Yeah, as a mean, as a tool.
as a tool,
So then you can have a graph.
the complete graph.
Yeah, and then of the complete graph, we optimize the graph. And then we can get X.
Oh, I understand. Thank you.
When we are making this marker, like we are showing the graph ones, we are creating arrows between x's in both directions.
Yeah.
But MRF is a undirected graph.
Yeah, so there is a different thing. So MRF is a MRF graph separate from SD graph. SD graph is a directed graph, but MRF is not directed.
Second thing, I understood completely the mathematics and everything. Just how when we are switching from that probability function to MAP, I do not understand like how this function came. Like why do we solve the only the posterior term, like maximize this? What is the intuitive understanding of this? Because I do not want to calculate probability. That's what I got it.
Yeah.
But
So, let me think. So you said that you don't understand.
I have joined probability.
Yeah, you know this one.
Which directly is now the only the posterior term. Like how the concepts are related.
Okay, so this one, right? Part here is MAP, right? So you don't understand this one to this one?
Like why people do this in order to like solve this problem?
That's a definition. MAP is a definition, maximum a posteriori. And this one is posterior. So by definition, this is the definition of MAP.
Yeah.
By definition.
Yeah.
Yeah.
Like why people do this? Like when MAP use why use MAP to solve this problem? Like,
Oh, yeah.
why
So,
posterior term only?
so you agree that this one is the definition of MAP, right?
Yes.
Then, but we don't have the posterior. We don't have the posterior. This one is something that we have, we want to do, but we don't have this. What we have is actually joint probability. So then I explain this one. This one is posterior, and this one is joint probability divided by the efficiency. Right. So, in other words, if because we don't have this, then we just use this one as a because this one is proportional, right? So because of that, then we can just remove this one because it's independent.
And coming in future lecture like this non-binary.
Oh yeah, we will deal with that soon. Hopefully today, but I'm not sure if we have enough time.
Thank you.
You said x x1 and x2 must be different. One is
One is good, it must be the what is
the level. One is the
not necessarily have to be different, but in this case, it's
yeah, in this case.
Yeah.
So I'm wondering if they're just the 2 point I one and two. And if it's in this section, this probability, if this is I then it's but now we cover it. And then we move on so we
no. It is just example, simple example for two pixels.
and what's the in the
If it is how many pixels you have? 8 pixels.
yeah,
Then you have to have 8.
so it's on the global.
Yeah.
Hold on.
Global, it's not local.
No, so
This is just example. It's nothing to do with that.
oh, okay. So if we our image is 800,
Then you have to have 800.
will be all.
Yeah.
Oh, the secret sound on it.
Yeah. So there is one x1, x2, x3, x2, and then x100.
Okay,
It's a global. You have to use all the pixels.
so it will just give the 8. Oh, we can make
For the because the cost, what happens if I can't eat?
So how you can count? But it's not saturated. You cannot count.
Or if it's not such a then
Yeah, it's saturated one. That's why I told you that actually this is simplification of this graph. This graph has to be zero for the residual.
Oh,
To be cut, you have to be zero.
oh,
Yeah. Yeah.
How we expected before or this?
Yeah. But it can be in different ways. Not necessarily box, but maybe some structural something depending.
So the packages we draw
Yeah, structural.
I guess this indicates that
Yes.
we need
No, as long as you can just keep the displacement of the points that you find.
Can I just check with you? So X is the label and D is the pixel value. Then beforehand you already know the function P, which is
You
the,
don't.
you know,
You don't know what. If P is, yeah, 5 or P, you don't know.
but you first you find that
FP, yes, FP we define. We have to define FP.
then but find like is it P like minus log?
Yeah, you can just transfer whatever that one. You exponential FP become 5.
Exponential. So it's like you self-select.
Yeah, so selecting 5 or selecting FP will be the same thing.
Oh, okay, I see.
Yeah.
Oh, okay. Okay. Can thank you.
The rabbit nearby the blue is far away. So here, so it is the storm of that's so it's I mean it's just so that's not just
比如说 CV2 里面有一个现象，就是非常，就是可以用那个，它不是 CV2 没有归在 CV2，我们感觉用 CV2，我们版本不一样，我们那版本那个 CV2 里面没有 CV2，它专利失效。哦，我知道，就是它有后一天的信用算就是在那个专利。那你说我说的话，我们只有说能不能用 CV2 里面的东西来，你就直接是 CV2 嘛，因为它别的呢，我们把别的那个。是那个 retrospective， 其实就两个部分，一个是 match， 一个是那个。然后 retrospective， 他把那个裁剪掉，我看那个是自己写，那个是那个明确说的不能自己，不能用。他自己他在那个 FAQ 里面写，你还是得要写自己。我写了，写了，是我太慢了。然后我想说那个没关系，主要是用每个写的，我自己写的那个玩意儿，还得做评。好。Just to be clear, for safety, for safe part. I need to write my own safety for the. No. Yeah. Impossible for you to. Point to action. Yes. Okay, so let's start our second session. There are a few things before we discuss continue our discussion. First is your CA1. So I just want to remind everyone the deadline is on the 8th, I think. So this one is the deadline. If I'm not forgotten, it's 5 p.m.
And this one, as I mentioned again, is a strict deadline. Means that if you cannot make it and then you have a late submission, it will be a penalty. 2 points every 24 hours. Another thing is that you cannot submit part by part. You have to submit as a whole. Okay. So if you submit part by part, we will consider the last submission to be your submission date or submission time. Yeah. I think that will be the best way. Zip it and then put it into one file. Because if you separate, then it will be, the different file will be in the different location and we will miss out your submission. Yes. I'm not really sure if the system allows you to do that. Yes, so the best way is to zip them and then submit once. That will be the safest way because otherwise we will miss out your submission or the part of your submission. Yeah. Oh, yes. Oh, yeah. If that's your question, whether you have files, right? Different files, part 1, part 2, part 3, and different 4 files, for example, if there's 4 parts, you are allowed to do that. But you have to then zip them. Okay, so don't submit in separately. Okay, and that's actually the suggestion that you put in the different files, because if it's put in the one file, it will be too large. Right, so separate them, but zip before the submission. Any question for CA1? Okay, so if there is no question for CA1, the second thing, what else is important? Yeah, so maybe CA2. CA2 is already up there, but I haven't announced it yet because I don't want you to get confused. But it is already online. CA1. Yeah, so this is CA2. So the deadline is November, 1 month from now. So this is exactly before the reading week. Okay, so this one is noise removal, exactly like what we discussed, is a binary labeling. And you have a pseudocode here. The pseudocode is actually in C, but you have to write in Python. So your code will be in Python, but the source, the pseudocode for you to follow is in C. So basically, this is the input and the output. And then this is a second part, which is depth estimation, which is multi-label depth estimation. We will discuss this soon after this. And then this one is again, this one is rectified, and this one is non-rectified. Then you have to use the equation. You will learn the equation hopefully today, if not next week. And this one is from video, and that's an advanced part of course. Well, so that's the idea. So that will be the deadline will be on November 11th. Any questions, comments? Anyone? Yes. Sorry, I cannot hear you. It is have to be submitted in November on November 11th. Yeah, Python. This one is the same for the same as CA1. Jupyter Notebook and on Python using Python. Any other questions? Okay, so if there is no questions, I think that's all for the announcement. Okay, so yeah. Okay, so now we have discussed about graph cards. And so we talk about MRF graph, right? MRF, which give you complete graph, complete MRF graph. And then you do the optimization or graph optimization. For this graph optimization, we solve it using graph cards. And another way to solve this is using belief propagation. I'm not really sure if I need to explain belief propagation. Well, it's very simple algorithms. Why not? So let's do it. Belief propagation. So the formulation of belief propagation is based on belief. Based on belief. This can be useful for many applications in belief. Pi xi and k phi I xi product of j neighbor of I and ji xi, and that's all belief. And message passing is the definition of this M here. That's called message passing. So this one is Mij xj equal to sum of xi phi xi psi ij xi xj product of k neighbor of I except j and ki xi. So it's quite complex. Look like very complex, but it's not really that much. So we will see later on what the meaning of it. Okay, so this is the idea of belief propagation. I give you the example, simple example. In graph cards, we have xi, previously we have a case of xi, x1, x2, right? So we have x1 and x2, and we want to know what is the label of this x1 and x2. And there's a connection there. So xi either foreground or background. So we want to do the labeling, the same as labeling in graph cards. So how can we do the labeling for this x1 and x2? In graph cards, we have to transform this graph into a ST graph, right? That's the idea of graph card. We transform this graph, Markov analytic graph, into a ST graph. Previously, we have T, T1, T2. But for simplicity, let's just remove this one, T1 and T2. Let's remove the observation for simplicity. So now, if given the two random variables like this, basically, we want to know the belief of x1 to be foreground. We want to compute the belief that x1 is actually foreground. And of course, we also want to know the belief x1 equal to background. And then if we have these two beliefs, then we can compare which one is higher. If the belief of x1 equal to f is higher than the belief of x1 equal to b, then the label of x1 is f. If this is the case. And if this is the case, when we do the maximization, not minimization, but maximization. If it is minimization, then the label of x1 is P, the background. Okay, so because the belief is easier to be maximized, then let's assume that our cost function, objective function is maximization. Not minimization, but maximization. So if it's maximization, then the higher the belief, the more probable the label is. Right? Okay, so let's how to compute the belief. A belief x1 is equal to f. We assume that x1 equal to f. So, and we want to know the belief of this. This one means that k is just a small factor, certain sorry, small number. Later on, I will explain what the meaning of k. And ft, basically ft is the same as this one. So this one is theta term. This one you can put it as ft. So for our case, right? And ft x1 equal to f and t1. And we know we previously define ft, right? Although in our case we try to minimize. So if you want to do the minimization, then you have to choose the smaller belief. And because you use ft and ft was meant for minimization, so we have to choose the smaller belief. That one different to this. So now we have M2 here, right? So we have MJI. So I, in our case here, I refer to 1 and J refer to 2. So J neighbor of I. So here say that J is the neighbor of I. So because J is neighbor of I, J is equal to what? What is J now for our case? J is neighbor of I. So what is J? I is equal to 1. So J is 2. Right? So because J is 2, then and J equal to 2 to 1 xi x1. There is no other neighbor of I. J is 2. J equal to 2. X1. So now, here, if you look carefully, I followed by J. So I here now equals to what? I equals to 2. And J equals to 1. So be careful with this. It's swapped now. So originally we have I equal to 1, now I equals to 2. Okay, any questions here so far? Right. And this one, by definition, is sum over xi. So this one is sum over xi. What is the possible value of xi? What is the possible value of xi here? Xi is either foreground or background. So I will explain that later on the meaning of sum. Okay. Now the next one is phi I. Phi I means what? Phi I, for our case, phi I here equal to 2. Means that we have to use M T x2 T2. Any confusion here? Any questions? Okay, so now there is for phi. For psi here, so psi here is actually similar or the same as our prior. Psi is a prior because that one is only evolved xi and xj. Okay, so this is a prior. So in our term, it is fp xi, I is 2, xj, j is 1, x 1. Right? The next term is this one. The product of k is the neighbor of I, but not j. What is that? What is k then in our case? K is the neighbor of I, but not j. I is what? I is 2, right? K is neighbor of 2, neighbor of x2, but not xi. What is that? Is there any x3 in our diagram? No. Means that that's it, right? That's not non-existent. K is non-existent. Okay, so for this simple case, we only have these two equations. And if you look at this equation further, what does it mean by the sum there? The meaning of the sum is that you have FG x2, x2 here, xi is equal to x2, right? So this one xi is equal to x2. So x2, you choose one of them. In this case, is x2 equals to f g2, fp, x2 equals to f, x1 equals to what? So x1, so remember that x1 here equals to f. So we actually already know that f1, sorry, this one, x1 here is actually assumed equals to f. Because of this, the beginning that we want to know the belief x1 equals to f means that x1 equals to f is given to us. So this one is actually x1 is we already know or assume to know that x1 equals to f. So that's what x1 equals to f here. Plus, because it's sum, right? Because of the sum sign, we have sum sign there. Sum over ft x2 equals to p, and t2 fp x2 equals to p, x1 equals to f. So that is the idea. So the idea is that we assume that x2 equals to when x2 equals to f, what will be the whole value here? And when we assume that x2 equals to p, what will be the value there? And then we sum them. That's the meaning of this sum sign there. Okay. And that's it. If you have this one, that means that you know the message here. And if you know the message there, you know the message here. This is called message passing. And then if you know the message here, then you compute with your data term, and then you can know the belief. If x1 equals to f, what is your belief? Okay. Any questions, anyone? So this is the mathematical meaning of this formulation here. Any questions? Well, the mathematical meaning is you have to follow. It's easy for a computer to do this. It's just a mechanical to make it as a function. But more importantly, I think it's the intuition behind this equation. What's the intuition behind? So the intuition is that it's really like your belief. Whether you believe, for example, right? If you want to measure the belief, whether your friend or yourself believe in an alien. All right. Some of you maybe not believe in alien. Some of you may believe in alien. So what does it mean by this belief propagation? This propagation means that if you want to know what is the belief of this community on aliens, then I can just first connect you with your best friend, for example. So your best friend yourself is X1, and I just want to know whether you believe on alien or not. And X2, I do not know, because I do not know your best friend. But then, if I assume that you are believing in alien, then I can measure I can try to find the message passing from your friend. So this one, the term here, M21, is a message from your best friend to you. What does that mean by your best friend to you? So it means that if you look at this one, it's a message from your best friend to you. And it depends on your FT is a person belief. It's not influenced by your friends. So this is your internal belief. That is FT based on your internal yourself. But FP is the influence from your friend. How close you are with your best friend. If you are so close from your friend, in this case X2, then this FP will be strong, will be high. And because whether or not your friend has belief, so this one in the blue line here, saying that what will be the FP if you have the same belief? So you believe in alien F, and your friend, this is you, X1, believing in alien, and X2 also believing in alien. So what will be the function here? If the function is high, for example, it is likely to be high if it is believed, right? If your friend is believing on something, it's like, or your best friend very close to you, FP means that if it is high, it means that it's very close to you. It's likely that it will be FP here will be high, right? So FT is your FT of X2 is the internal belief of your friends. How strong he believes in himself or herself on alien, right? So that is FT, and FT here, B is, for example, not believing in alien. So this one is not believing in alien. Your friend is not believing in alien. And this one, FP here, is that how likely that your friend and yourself to have different beliefs, right? If it is, if it is low, for example, if there's two different, and if it is different, it is that it's low. Your friend is not influencing you that much, it will be low. If your friend is influencing you a lot, then it will be high. So basically, this is the connection between you and your friend. And it's also influenced by the belief of your friends alone, without influencing by you. And this message here will be sent to this equation here. So it will be sent to this equation M21. Means that what is the influence of your friend to you? And here it means that the influence of your friends to you, and that will influence the belief whether you are believing in alien or not. Of course, your friend is important, right? Your friend is important in influencing the belief, and to one is your friend. It influencing you, but you also have your own stance, whether you are strong confidence or not on yourself. If you are strongly confident on yourself, for example, then it will be high. If you're not strongly confident on yourself, then it will be low. Okay, so that's the idea, the intuition behind this. So you have your own confidence, but it's likely you also influenced by your friends. And of course, here, your friend is not just X2, maybe it's also X3. And maybe X2, your friend, also have another friend. Means that we have X4 here. And if your friend is very social and very chatty and so on, and with many, many friends, then it has many friends. And you are not so chatty, you only have 2 friends. Right? But the whole social network here influence your belief. Okay, so that's the idea of belief propagation. So, and the mathematical of this mechanism of how you being influenced and how your friend is being influenced by you is described in these mathematical equations. This is very powerful equations used in social science, used in physics as well. And it is more general than graph cards. It's not necessarily to be, well, it is based on the graph, but it's not necessarily to be, it can be any graph, basically, to be used in this representation algorithm. Any questions here, anyone? Okay, so that's how this belief propagation. I will not go deeper than that, but this one is very famous algorithms. So if you're interested in this, you can look at the on the internet. It is proposed by Julia Paul from UCLA. Okay. Okay, so that's all, I guess, for this one. Right. So I stop here for this graph optimization. So now, if you have, do you have any questions? Okay, so if there's no question, let's move on to our problem. So our problem is a depth estimation. Depth from rectified images, using Markov field and graph paths. The optimization is graph paths. Okay. Now, the motivation is this one, right? Oh, by the way, the color here is just for illustration. There's no color actually. Depth doesn't have color. Depth is only distant, only single value. This color is only just for easy visualization. Red means nearby, blue means far away. Okay, but the correct one, the proper one is actually this one. This is the proper one. So this one is grayscale, right? The value that your output should have is actually the grayscale one. So now, how we can compute this? This is the question here. From these 2 images, rectified means that if you want to know the corresponding pixels of this peak here, so that it's a cone. If you want to know the corresponding point of the cone, the tip of the cone, then you can just draw a horizontal line, right? The horizontal line will give you the corresponding points. So the same as what I illustrate here. So illustrate here, you have to draw the horizontal line or the same y to find the corresponding points of the target pixels. Okay, so that's the idea. And the solution is using Markov field. So MRF is the solution that we using. And this is described as now G is the depth. So T here is a depth map. So this one is a depth map. Depth or disparity. Let's put it disparity. Disparity map. Okay, it's a map. T here is a map. It's a matrix. It's not just single value, but it's a matrix. It's a map. Okay, so T is a map. Equals to argument mean of all possible values or possible combination of the map of T and sum of x. X is the location, so it's a pixel location. It's a pixel location that you want to compute the depth. And you have as T x bar T x bar I prime I will explain the meaning of this later on. Plus lambda or W sum over y pixel y, which is the neighbor of pixel x at p dx dy. Okay, so this is the Markov random field for depth estimation. So this is part 2 of your for your CA2. So now what is the meaning of this? We know that this one is a pixel location. Dx1 is the depth at that location. The depth or disparity at that location. I is input image on the left, for example, and this one is input image on the right. Okay, any questions about the definition of these variables? Y is the neighbor of the pixels next to x. That's why. Any questions here, anyone, for the variables? Please ask if you don't, because otherwise it will be confusing for you to follow the whole discussion. So T parenthesis here is a range. So T here is D min until D max. And this one is the number of your label. In this case, it's multi-label. It's not binary anymore because it can be many of them. This is multi-labels Markov random field. Any questions? So now the next thing, if there is no questions, is that the definition of this part here. Right? That part is called data term. So this one is again to remind you that this one is called data term. So what is the definition of the data term? Data term, okay, what is the idea of data term? Anyone? What is the idea of the data term? Okay, so I will give you the equation here first. I prime. So we want to minimize. So imagine, remember that we have triangulation in this case, right? That estimation is always something to do with triangulation. And we have this image here, the image there, and then we have C prime, and then we have capital X, and then we have x bar, we have x bar prime. So this one is I, and this one is I prime. And we want to know the depths. We want to know the depths. For example, if you focus on I, then actually we want to know the depths here. So we want to know the depth of that. Okay, so the depth from C to capital H. That's the depth that we want to estimate. Any questions here? Okay. So imagine that we have that one. And I will give you the equation first here, but then we can discuss the meaning of this equation. Rx is the RGB value for that location X. So Ix is the RGB value, the pixel value for that location X on the left image, I. Minus I prime X bar plus D X bar squared. So what it means by this, remember that this one is for rectified images. Means that we no longer have exactly like this one, but we convert this one into a rectified version of this. Means that we have I, and then we have I prime. For example, here is the pixel of X bar, and we have the horizontal line, right? And we want to find X prime. X prime is something that we want to find out where it is. And basically, if I can, here is the case, X minus I X prime have to be, if I can find this, X prime have to be equal to what? Anyone? Have to be equal to X and X prime. I found X prime already. Anyone? What is the answer for this? What is the value here? Ix, I is one for it is not rectified. So you have I there, and then this Ix, and I found this. This I prime, so this I prime X equals to what? Equal to 0. This is, it means that we found this, and if we found that, it will equal to 0. Okay, this is the perfect condition because we want to minimize. But unfortunately, we do not know X prime. We do not know X prime. We do not know this. So that's why we have to search along this line. We have to search along this line here. And searching along the line means that we have to sum this X. So where is X? In X prime, in I prime here, X means that perhaps this one is X here, so that's X is here. Okay, so we start from there. So that's the meaning. This one is the meaning of I prime X bar. Agree with me? So if we have I X, do you think that it's the case that this is the same? Are they the same? Again, does it hold here? Does it hold here? Is it yes or no? Who say yes? Can you raise your hand if it is yes? Who says that it's no? How many of you say no? Okay, so why is that? Why is that? Is it why is not the same? That's correct. It's not correspond to the. So if you look at the this one here, if you look at the one here, x in the location is actually not correspond to the x on the left. So that's why it is unlikely to be the same. It can be the same in some cases if it is uniform, right? If the picture is uniform, left and right, but in the real world, it's unlikely to be the same. So the sign point will not be equal. Then we have to move this one, right? We have to shift it to that direction, perhaps. Shift it to the right direction. So this one, d x bar, means you shift. This one is a shifting point. So if it is the first one, the first candidate for dx bar is d min. So if you move here according to d min, so this one is actually d min. X plus d min. You shift. And the distance is the shifting distance is d min. But shifting d min is unlikely that give you the corresponding point. You will have to, well, we do not know. That depends on the equation here. But if it is 0, then it's likely to be matched. But if it is not, then in any case, you have to scan d min, d min is d1, right? Perhaps d2, d3, d4, d5, and so on and so forth until you find d max. Means that if you use all the possible labels here, it means that you search all along the way until you have all this error function. So for every pixel here, for every candidate, you will have an error function, error value. Okay. So if I can give you the illustration, is that you have ft here, and then you have g here. This is d. So this one is d min until d max. Is that understandable? So hopefully the error function that we can gain from this one will give you something like this. Hopefully, this will be ideal, will be perfect. Right? But of course, we do not know. But maybe it's not something like that, but something like this. We do not know. But regardless, this is something that we want to obtain. This is something that we want to obtain. The cost for every possible depth value, because this one is the depth value or disparity value. Is that understandable? If you don't understand this part, so then I can explain more. So again, this is the task here is to find at the whole curve here. This is data term. So in other words, if this discretized, it is in your program, so discrete, the discrete version of this graph will be, for one pixels, for one target pixels, you have for one target pixel, right? You will have FD. It's likely that you will have a factor here. Yeah, so you will have a factor. So the mean here. So if you, well, basically you have a factor here for FD factor. And this one refers to FD the mean until FD the max. So this FD factor is something that you need to obtain. It's the same thing as this one, but it's now become discrete. So this one describing for one pixel what will be the cost of all the possible depths. Any questions? If you get confused with us, then I can explain more detail. No questions? Yes. Yeah, go ahead. That's a good question. We do not know. Well, for this rectified image, it's simple. For this rectified image, start from zero. Start from zero. But you have to go to the right and to go to the left. For this rectified image, you have to go to the right and go to the left. And to the left, it doesn't mean minus because there's no minus steps. So even though it's right on the left, you still have to count positive in a positive numbers. But you have to go into two directions until you scan all the whole image, the whole X resolution. Yeah, a good question there. Yes.
That down is the single pixel and also down is patches of.
Oh no, we don't really use patch anymore. Remember that you use Markov random field. Markov random field doesn't care about size anymore. And that's the beauty of Markov random field. Even though there's a single pixel operation, but it's actually already, global optimization. We don't use patch anymore. The patch is done automatically by Markov random field. Yeah, another good question. And yeah.
So when you so from PD to feedback exactly from balancing the horizontal line.
That's correct. Yes. Balancing the horizontal line. Okay, any other questions? Yes. We do not know X prime. That's why we have X prime is somewhere here, but we do not know. We just don't choose now. We just give this factor. We just draw this graph. Yes.
We will have different T, the magnitude to result in the same FT.
So T means for the rectified image is actually start from zero to whatever the max here. I think the max is you can assume if it is resolution is around 200, then it should be 200. And you keep this in this range. You don't change. Yes. Yeah, that's okay. Don't worry about that because the optimization will be done later by graph paths. So even though there are many local global optimum here that are the same zero, for example, don't worry about that because the optimization will be done by graph path, by Markov random field. Globally, not just pixel level, but globally for whole image. So that's the point of global optimization that I explained a moment ago.
The magnitude will play a role in
the second term is also local. It's just neighbor of each other. It's not global. The second term is local. It's just next to each other. But later on, when you use graph path flowing the water to the pipe, that's become a global. So there's the beauty of this mathematical expression. The mathematical expression is a local expression, single pixel and neighboring pixel. But then when you combine this into a graph, into a complete graph, then the optimization becomes global. And the choice of the depth is automatically done by optimization. Yes, a good question. So give me the opportunity to explain this. Again, the expression here is local. The Markov random field expression is local, but when we do the optimization, it becomes global optimization. Again, the global optimization is done by flowing water from the source to the sink, connecting all the pixels, connecting all the nodes. Any questions here? Any further questions? Okay, so if there is no question, that's how we define FD for each pixel. So for each pixel, we will have this function here. Again, then you have to discretize this. But your imagination is this kind of graph of each pixel. So that is FD, the first term, the data term. Now, how we can define the second term here, right? The second term is FP. How we can define FP? So FP is much simpler. FP is Dx, Dy. What is the intuition here? What happens if the two pixels next to each other, X and Y is next to each other? What happened with the depth in this prior? What is the intuition here? They have to be encouraged to be the same depth. How we can encourage them to be the same depth? It means that the distance between Dx and minus Dy have to be small. We minimize the distance. If they're the same, then it will be 0, and that's something that we want. Again, the depth here is a single value. So that's why you can make a power to 2 or quadratic. So what is the imagination of FP? FP is also for FP for every single pixel, for every single pixel. But FP here is independent from your pixels values, independent from your image. Right? So there's no image observation here. So it's independent from our image. So it's done once. So you define FP for every pixel once. And what is the FP for every pixel here is a matrix. So FP is a matrix. A matrix that has this form. So you have Dx, and then you have Dy, 2 pixels, regardless. So then you have D1 or dV, D2, D3 until Dmax. Maybe Dmax here is 10. Okay. And then you have D1, D2, D3 until also D10. And this one is the subtraction of the two, D1 multiplied D1. So this one is likely to be 0 here. Right? And this one, the next value here, you just do subtraction. So it's likely to be a symmetric matrix. So this one again is a 2-dimensional matrix for FP. So if FT is a vector, FP is a matrix. And then you just put these two values for every pixel to the GraphCut package to do the optimization. And if you do the optimization, then you will get the depth value for every pixel. Any questions here for the definition of FP and FT? So again, if you put this graph, this has become full graph now, into the package, into the GraphCut FT graph, then you will have the output as this one. No, it's a depth. Yes. So that one, here, right? T is T until Tmax, T1 until T10. The possible value of the depth. So in that case, in your case, it's from 0 to 200 or 0 to 300, depending on how much the max. What is the maximum or disparity for your case for your image? The final thing I forgot to mention is this one. Lambda. Lambda is a weighting factors for data term and or prior term. So if lambda is large, means that you are prioritizing the prior term, means that you are prioritizing the connection between neighbors. So it's likely that if your lambda is very high, then it will be not sharp. Your depth will not be sharp. But if lambda is too low, your output will be noisy. So be careful with lambda, setting lambda. So lambda is to control the connection between pixels, the smoothness constraint. If it's too smooth, then it will not be sharp. But if it is not too smooth, then it will be too noisy. So be careful with this lambda. Next week, we will learn more about lambda, how we can define better lambda. But for now, in your experiments, you just choose whatever you want. You change lambda equal to small number, 0.1, or lambda 10, for example, and see what happened in your results. Okay, any questions, everyone? Again, this is the definition of the data term and the prior term for part 2. So we have part 1 and part 2 solution already. Any questions? No questions. If there is no questions, I think that's all today. And I will see you again next week. Thanks, everyone.